How do we define what it means to be continuous? This graph up here clearly has a jump discontinuity when x equals 1. Now, in a calculus class, you probably define continuity by looking at maybe limits from the left, limits from the right, and we could do something similar in this series. By the way, this is day 19, and let's learn real analysis on TikTok. But we haven't actually talked about limits of functions. We've just been working with sequences. And for us, we're going to just define continuity by looking at sequences, and it's a pretty cool way to do it. Imagine you had a sequence of input values approaching 1, but from the left. Well, your output values would be steadily approaching the value 3, which is not the same as the function value at that point. Note if you plugged in 1, you would go all the way up to 4.5. And also if you converge to the input value of 1 from the right, you would get a different value than you got from the left. Here's the careful definition of what it means to be continuous at a certain point in our domain of a function. And this is a perfect example in mathematics where we do a ton of work, like 18 days of a TikTok series, to understand what is a sequence, what is convergence, and then take all that we know and say, well, we're just going to define continuity in terms of some statement using convergence. Using sequences because we're so expert at using them and we have all these wonderful properties we've been developing. And so for instance, because we've already proven using something called the main limit theorems for sequences that if xn converges to 3, then xn squared is going to converge to 9. No matter how we approach left, right, doesn't matter. That's going to prove that this function here, given by f of x equals x squared, is continuous at the point x equals 3. That's it. That's a complete proof. We did all the hard work earlier when we were proving, for instance, that the product of convergent sequences is again convergent. All of the hard work that we've been doing is starting to pay off. Look at how easy that proof was. Later, once we prove the intermediate value theorem, it's going to have all sorts of applications about solving equations and knowing that the solutions exist. Next class, we'll take a look at weird functions like this and study, are they continuous? Are they not? How could we tell?